I'm Sylvain, Bertrand from IHMC. So we're going to do the next tutorial. So it's going to be about like the core that we've been working on, the controller core that we use inside our working controller for Atlas and Valkyrie, for instance. We also use it like for quadruped. We started that recently. So we're going to go through like today like a tutorial that is very likely like way too long to fit in an hour, but everything is online, and hopefully you should be able like to get started today and to be able like to finish it later if you want to. Before, just I saw that on Slack. Everybody saw the image, and that thing starts. I want something that works. That's. Sorry about that. It starts good already. Okay, I'm gonna restart that. But yeah, on Slack, Brooke posted like she found like some looked like a speaker in the parking lot. I'm not sure if like the owner found it. Anyway. Okay, so for today's tutorial, so it's not going to be the same quality as OpenSim. Sorry about that. That's my very first tutorial, and that's the first tutorial from IHMC. Hopefully, it will get better in the future. So, however, I have Brendan, Georg, and Robert. Three of them know about the control core. So if you have questions, just feel free to ask any of us, and we'll do our best to answer you. And what we're going to do is, the very first thing, so we're going to go on the GitHub. Oh, yes, thanks. All right. OK, so we're going to go on the GitHub repo of the tutorial. So it's github.com/ihmcrobotics/dynamic walking tutorial 2018. And once you're there, you just direct yourself to the wiki, and that's where the tutorial is going to be. All right, and we'll start with the step one. So it starts from very scratch. It's like, so our software is not an executable that you can download and install on your OS. We don't have the manpower of doing so. So we still work everything like, so you're going to be like installing like Java, because we do everything, or at least we try to do everything in Java, and Eclipse. Java is pretty good. And if you don't believe me, you can talk to Jerry. He'll give you a half-an-hour lecture on why Java is amazing. So yeah, the first step is about is going to take you step by step how to install all that stuff. So I'm going to let you do that. At the same time, I'm going to give like just a quick idea, a quick summary of what is the control core. So it's pretty much like we extracted. Sorry, let me start over. The walking controller is based on the whole body framework that uses at its core a QP solver, and the outputs like that finds a set of desired accelerations for the joints and the desired external forces that you want to apply. So for instance, like on the feet, how much force you want to put on your feet, such that those two quantities can now be then fed to an inverse dynamics calculator, and that can then compute your desired torques that you want to send to the robot. So the first thing we did was pretty much like to extract those two guys together out of the a working controller, and to have like something that is well defined, that is easy to use. And we discovered very quickly that it would be actually very nice to also enable two other modes besides what we call the inverse dynamics. So we have pretty much the controller core does the same thing, but in the velocity space. So it does inverse kinematics, whole body inverse kinematics, and it also does what's called virtual model control, which is like it's pretty much like a generalization of like the methods that some call the Jacobian transpose methods, where you say you want a virtual force at your end effector, and using the Jacobian, you compute what should be your desired torques at the joints, and so we have those three modes in the control core, and really the goal was like to simplify as much as possible the API of that controller, such that somebody who knows the IHMC software environment, let's say, could program a rather complicated controller in a few days. So that was really like the objective of that, like to speed up development. On top of that, of having the three modes, there is something also that is somewhat, that is very error prone when you work on a controller, is when you write your feedback controls, like those simple PD controllers that you do. So the ones, when you do that on the joint, it's relatively easy. But when you want to do it at the end effector in task space, and maybe you want to apply some selection matrix, you don't want to control everything, and maybe you want to do like some kind of very weird control strategy where you want to control that with respect to another object, blah, blah, blah. You can get really complicated, and that part can become then extremely easy, like to make errors in there, slowing down development and slowing down pretty much exploration. So that's also like that component of having like feedback controllers. We also included that inside the whole body controller core. Once again, like to reduce the amount of bugs you can potentially put in your controller, and to speed up, like to reduce the time you need, like to create like a complicated whole body controller. I'm just wondering, how are we doing on like the downloading Eclipse, Java, and all? Like, how many people have downloaded Java and installed it? How many have not? I guess that might be a better question. Can you help him, Brendan? Thank you. Is there someone else who has a problem with installing the JDK? Okay. What about Eclipse? Who is not ready with the Eclipse? Okay, yeah, but it's good. Okay, good. All right. And what was next? Thank you. Yeah, I made the decision of doing only Eclipse, because if you know your stuff with the integer, go for it, but I won't help you. Robert can help you, though. He uses it. So we had the JDK here. Oh, yeah. I love it. I don't know.
Slack channel so that we can actually have a log of things that people run into.
Then they could pull issue on the GitHub. That's the best. I think that's
well, I mean, there's simple things like he's having trouble importing something in Gradle, so it's not really a bug. It's just if you encounter a bug, put it on GitHub. But like it's just something like where you need help on, that would be
Is there a channel specific for that?
for demos. Duncan said there's a channel for demos, which this is one.
What's the name of the channel?
Probably demos.
Okay. Hey guys, if you're encountering some issues, can you select them on the demos channel? Apparently there is a channel for demos.
Keep track of them so that way we can incorporate them into our tutorials and stuff later.
We oops. I'm going to stand by. So right now we're gonna spend like some time on step one, make sure like everybody who wants to do that tutorial at least have their setup working, because the next steps are gonna be much easier. So just want to make sure that we've got that right. So step one. Yeah, we really love error printouts. So if you see like when you run a program that you have some errors printing out, just ignore them. If everything is running, it's good. Is anybody else having issues? Who's reached that? Okay, we start getting some. Okay. All right. So I'm gonna give a quick word on what's going on there. So first of all, that's what we call the simulation construction set, SCS, pretty often. And so that's the simulator that we actually Jerry wrote a very long time ago, and we've added components to it. So every of our robot simulations, we do them in SCS. It's got pros and cons, but overall we like it very much. Like for instance, the thing that is really nice is like you have everything. You have an easy access to your control variables. So we have like something that we call your variables. Those are just, we use them to represent like simple primitives like double, integers, things like that we can easily declare in the controller. And the simulation is going to be able like to find them. And thanks to that, you can actually like plot them or even like change them on the fly, such that if you want to do some tuning, you can just update, change your gains or things like that. You have so that part will be useful later. So there is a search box on the left side where you can, for instance, like search for variables. So here we don't have, we mostly only have like the state variables of the robot. There is no controller there. And that's just like very much like just to show like the basic features of SCS. Does anybody need more time to finish the step 1? Okay, if I don't see any hands raising, we're gonna go to step 2 then. You need, what's that? So nobody needs more time. All right. Okay, we're gonna go to step 2. So so the step 2, so now it's pretty much, so we're really gonna go through step by steps. And also like these tutorials, we're gonna go through examples. So examples that are already working, and the code should be like commented, like to help you like understand what's going on in there. And so pretty much like the goal there is like to get you like an easy setup, and if you want to mess around, like just play, like change things in the code, just play around and see what's going on, try to understand like that. So the second step is just like we're just gonna run like a simulation of a simple robot arm with the 7 degrees of freedom, and that has a controller this time, and the controller is just like the most basic controller we can come up with, just PD controls on each joint that outputs desired torques that we then feed to the robot.
You have a model of your robot in Java. Can you actually load also your edit models?
So yeah, so we're not going to see that in there, but like for instance for Atlas, we didn't write it in Java. So we have like an SDF loader. So we do only SDF so far, I think. We have to convert your DF to SDF, I think. So I just want to make sure that we go through the essential steps and try to provide as much explanation of what's going on, but I'm not forcing the pace to be really fast. And apparently, I think we're like maybe also like overloading the Wi-Fi, maybe, because like usually it doesn't take that long. So for the step 2, are you all stuck like me, like downloading jars, or? Huh?
I think it's because we have 150 people trying to use our network at the same time, is what's going on.
So who's got through the first simulation, the first robot arm? Anybody else need some more time to get there? Okay. All right. So here, like some of you asked me, like, hey, I don't have the time showing up in the graphs like in the first simulation. It's just because I didn't add it by default. So for that, so at first you have like to create a new graph here. So that's a new empty graph that we just have now to plot variables in there. And to plot variables, we're going to search for them. So for instance, we're going to look, let's say, for the velocity of the joint. And for instance, we're going to plot the velocity of the shoulder yaw. And let's actually look for the desired position of the shoulder yaw. So it's pretty. Oh, I guess I should have done desired velocity actually. And you can, if you right-click on the graph, you can actually like remove variables. So that's what I'm going to do. I'm going to remove the desired position there. All right. And so now we can see like the tracking, for instance, of the shoulder yaw, like the tracking of the velocity. If you're looking for time, you can you just search for the variable t that you can plot, and you have your simulation time. Why 10 kilohertz? Oh, so nothing in those simulation is properly tuned. It's just tuned such that it works, and you can run it and see what's going on. So nothing is optimal. And let's look, let's say, for the gains, for instance. So I'm going to do the KD. So at the bottom here, you have like some a plus and a minus, and that allows to add like a tab in which you can add entry boxes, as we call them. And there it's like kind of the same system as the graphs. You can drop a variable there, and now that variable is saved here, and at all time like you have access to it. So usually it's a good spot to put gains in there. So let's say like for now, like I'm gonna set the gain, the D gain to 0, and I was expecting it to go bad, but okay. Man, that thing is like simple PD controllers. They're very good. Let's do that. All right. And now, so yeah, the gains are extremely low, and yeah, it's going all wonky, I guess. So yeah, so pretty much like you can just show that you can play with the gains on the fly, and you can also like stop the simulation at some point, go back in time, and change a variable at that point, and start simulating again from that time. And if all your robot state is saved as your variable, all your control variables are saved as your variables, that means like everything gets restarted from that point in time, like properly. All right, so now we're gonna go like to the next step. So I think it's, I believe it is step 3. And we're finally, like in that step, we're finally gonna include the whole body controller core in that simulation. So we're still gonna do only like control in joint space. And we're gonna see how it's different and how to actually like create the whole body control core for that. Oh, I am sorry. Yes, indeed, it is number 4. Thanks. Okay. Hey guys, just so we're trying to figure out like why importing projects is so slow. So if you're having a problem using like Gradle, like importing a project, if it's taking forever, just cancel in Eclipse. So you can cancel like there's going to be like a progress bar here that you can click on, and you can ask it like to cancel. Just cancel it, and what you do is you go using your Explorer, you go in the project, there's the build.gradle file that it's called, and in there, let me go actually in the fresh one. Ah, come on. In there, there's going to be like those 3 lines. You can, it says temporary. So we thought that would help for today, but actually it does worse. So you can just remove those 3 lines if importing for you is slow, okay? So it seems to be to speed up quite some the. What up? All right, so we're already like reaching the end of this tutorial. So I'm gonna make some additional comments on what's going on in this step 4. So as I said earlier, like in that simulation, we're pretty much doing the exact same thing as before, but instead of running like simple PD controllers, we're using now the whole body controller core. By default, when you run the simulation, it does inverse dynamics. However, if you go in the main simulation Java file, you can see that there's actually like a mode that you can change here, that variable, and you can see that if you use, so there's I added after like the steps on the wiki, there are a few Eclipse shortcuts, and the one I'm using right now to have that pop-up window is in there. So I just control space the auto completion, and there that shows you in there that you have like the 3 modes that I was talking about. So inverse dynamics that is running now by default. Second one is inverse kinematics. So we're gonna switch and see. Shoot. So now, the simulation, actually, the physics is deactivated, because when you run the inverse kinematics, the main goal is pretty much like to compute your desired velocities and to integrate them to have like, to be able like to use that in a whole body IK solver to get whole body desired position. So there we're just like using SES to visualize what's the solution being on the output of the controller core. So that's the inverse kinematics, and there's the last one. Oops. Virtual model. And this one, pretty much when you run the simulation, this simulation using the virtual model control, it's pretty much doing the exact same thing that we were doing before, meaning PD controllers at the joint level outputting desired torques. The virtual model control is going to make a difference only when you have contact with the ground and you need force distribution, or when you want to control in task space and end effector. So I invite you to. We're not going to finish to go through all the steps here, which I was like expecting actually. Here you have all the steps needed to go all the way to using the whole body controller core to make a simple robot walker. So it shows you how you can use the inverse dynamics mode with the simple biped robots, and how you can control the swing foot to swing following a certain trajectory in task space, and how you can switch on and off a foot to use it for support of a swing. Once again, that simulation is like, so I made that controller in like, I don't know, like 2 or 3 hours with the documentation. So that's just to show that you can, and nothing is tuned. So you can go through it once you know, like the framework, let's say. It's very, very rapid, like to bring up to life like a new controller. And once again, like that's very, so compared like to the state of the art, there is absolutely nothing new inside that whole body controller core. The thing really we're trying to push is like to be able like to be much faster when experiencing like new controllers on different systems. So I invite you, for the people who are interested in continuing this tutorial online, I invite you like to submit issues on the repo on GitHub if you have like any problem, like once again with if Gradle is giving you a hard time or whatnot. Feel free like to submit issues. I do my best to get you going. And do I have to add something else? Oh yes, there is also once you're done with the tutorial, there's a page, what's next, how to make a project from scratch. So if you have the crazy idea of maybe using a software and you want to create your own Java project, those are the very first steps on how you can get a Java project set up with those that can depend on no software. And you have a very, very brief summary of like the different libraries that we used in those examples. And I think that's about it. Does anybody has questions? No? Okay.
So this basically is only the whole body control framework plus the simulation tools. If you want to run it on the real robot, what additional components do you need?
Okay, so the question was like, is that tutorial only about the controller core and the simulation? And if you want to run on the real robot, what do you need in addition to that? So the focus was really on the controller core. The simulation, I had to introduce it because that's what we use to demonstrate the controller core. To be able to run on Atlas, on Valkyrie, you need much more than that, obviously. So we have like a library of tools like to do like filtering and state estimation in general. And after there is also like the whole low-level like API to talk to the robots. There's quite a few things.
We do have a lot of open source packages to write that have these sensor processing and all the output writing features that it takes to run on a real robot. You still have to implement plain. Okay, so I have these set of core commands that you can use the whole body controller for. How do I then map that to an actuator? That's something that's left up on the implementation layer that we don't really. We have building blocks for it. So if you wanted to do like Ethercat communication, that's also open source packages that we provide. However, you then have to implement that for your motor. But
Yeah, like Robert said, we have an Ethercat library if you happen to have an Ethercat robot. We have a ROS control library if you happen to be one of the unfortunate people who was brave enough to make ROS control run on hardware. But yeah, like the actual systems integration is real hard, right? So it's hard to do that in a general way. I don't know what motor drivers and comms protocol you're using on your robot.
So yesterday when we were discussing, you mentioned the fact that you guys support ROS 2.0 or at least ROS 1.0. I think that you have some components, right? Which you have a library which wraps around the whole body control framework immediately, and then you just publish, and then you have a system which just accepts the commands and distributes it to the actuators. That could be the interface. So,
our walking controller that we run on Atlas and Valkyrie has a set API for how you communicate with it. That's a little outside the scope of this tutorial.
So to add on to that.
Well, can you repeat?
Yeah. So the question was, we've mentioned in the past that we have some ROS 2.0 and ROS 1.0 support. And so how does that work if you wanted to use that to talk to a real robot from these tools? So the short answer to what Robert said is that we do have a ROS API, but it is a high-level API. So it's things for like footstep planning or end effector positions and like whole body manipulation tasks. Our controllers are what you would call a real-time feedback controller. And because ROS 2.0 is nominally real-time, but ROS 1 is not. So you would not be able to do something like expose a handle for torques and then send torques over ROS control because you probably would not have a stable controller. Does that answer your question?
sort of, what I was getting at is like you guys have a library that instantiates in an easy way on Node, and then because this is Java, right? And
Yeah.
we have C++, and we
Yes.
want to feed it to some C++ node that receives the configs, receives the messages on the configs. Just a mechanism. If you have a mechanism built into this, that just creates a node and
We have so we have APIs that publish and subscribe over ROS but it's high level stuff. So you get feedback of the robot, like the robot configuration and the pose and stuff like that. And then the stuff, and it can be from it's fully ROS compliant, so it can be Python or C++ or whatever, but it's all over publish subscribe. It's purely ROS topics, and it's purely like asynchronous, non-real-time stuff. So you would not be able to, you're not interacting necessarily directly with the whole body controller core, like you're not sending necessarily the spatial feedback commands that we outlined here, but you can send like slightly higher level commands. End effector poses and footstep plans and stuff like that.
Okay. I mean, the thing is, for example, there are several teams, I'm sure here, including us, who just use only C++.
Yeah.
So we don't just want to come here and have a look at what you guys are doing and discard it. If we want to set up some projects to leverage your tools, but then interface them in a nice way with our real-time control framework, which is only C++, what would you recommend as the best means to do this?
So
if not over ROS.
So I think maybe at what level do you want to communicate with our tools? Like which?
I mean, pretty much he's saying that representing a tools that he has no idea how to use if he's not using Java.
Yeah, I understand that.
Should I describe like very quickly like the setup?
Yeah.
So we have one Linux process communicating with all the drives, all the actuators. It's like a low-level runtime engine. And then the only thing it expects is at 1 kilohertz or 400 hertz or whatever, the set of 12, 18, 20, whatever, and number of torques that you need.
Right. So, and what I was saying is that our stack will not output at that low level over ROS. We won't work at that level over ROS because you can't run ROS 1.0 with a real-time guarantee.
But what about something like LCM or some other library that does shared memory? Do you have any facilities for shared memory over Java to something else?
Not currently, no.
Okay, because that would have been exactly the solution, right? If you have something which is going over shared memory or like protobuf, which is actually nice. I'm not aware, maybe someone can correct me, I'm not aware if protobuf supports Java. If it does so, this should be actually the perfect means for this.
We looked into using protobufs, and we actually landed on using DDS instead. So ROS 2.0 is built on top of DDS. And in fact, the pub/sub implementation for ROS 2.0 is simply a bunch of namespace and partition conventions. So we support raw DDS, and we also support ROS 2 conventions on top of it, and you can very easily implement shared memory or real-time intra-process over UDP using DDS. So those are options that are those are things we're looking at doing, but it's not in the current version of the software.
Okay, so we'll just have to wait for updates regarding this, okay.
Yes.
All right, thanks.
All right.
I think it's worth mentioning that this was very recently being extracted, so that's an ongoing effort.
Yeah.
So the kind of package communication stuff that you're talking about is something that we are actively working towards, but it's a relatively recent effort.
Okay.
And I think it was also beyond showing like a Java tool that it's like a programming tool. I think it was also maybe useful for you guys to see what kind of solution we came up with within our control framework to try to optimize our development effort, optimize our workflow. And I think that might be also useful in itself. So yes, that's it. So what's next? Food?
So I think we're done.
Yes.
Lunch is here.
There's some lunch, there's some bows out in the lobby. So thanks everybody for coming to this tutorial. We're kind of done for the time being. As Sylvain mentioned, this is all available online. You should be able to kind of continue it, and we'd really encourage you to do that. If you have any questions, kind of high level, how we do our software architecture, anything like that, how this works into Atlas, feel free to grab us during lunch. We're going to be around for a while. There's food in the lobby. I guess we'll be back in around an hour. Is that right? I'm looking at the two people who are then doing a tutorial.
For 17 minutes from now, so.
Okay, let's say 1:30. Cool. Does that sound good? Does that give you guys enough time?
Yeah.
Okay.
Thank you, everybody.
Okay. Full screen. So just like this, I guess, huh? This is good.
Yeah, actually, can you the juliarobotics.org/tutorial? Oh, we're gonna want the URL. Yeah, let's start here.
So yeah, 1, 2, 3, 4, and so on. What's up with this one? Okay, 7. This one can go. All right, so I've run everything for the first 3 ones. I've restarted the kernel. I've cleared all the outputs for all the notebooks. So. Okay, and I was gonna do this. Yeah, so I will stand where? Oh. Yeah. All right, just start it whenever you need. Yeah, I guess so. I mean, there was the bell thing, so.
Hi, everybody. Testing. Maybe I'm actually free. Maybe I'm not turned on.
No, we're
My standby is set off. Is that good? Does that mean off standby?
That seems better. Hey, there we go. Okay, cool. Hi, everybody. We're going to get started. I know some of you are still eating lunch, and that's okay. Cool. Thanks for coming. There's really a lot of you, but this is going to be fun. So my name is Robin Dietz. I work in the robot locomotion group at MIT. I'm a PhD student in my, let's just say, ALOT year. This is Tuan Kulin, who's also a grad student in the ALOT -1th year in the robot locomotion group, and we both work on humanoid robots and trying to do things like solve contact-aware planning and push recovery. So making the controllers that we run on Atlas and Valkyrie and robots like that more robust, more reliable in the face of literally any kind of disturbance. But that's not what we're going to talk about mostly. Today we're going to talk about Julia. So I want to introduce you to the tool that we've been using to do a lot of our research recently, why we think it's worth writing a whole bunch of new code in a brand new programming language that isn't even done yet, and what you might expect if you try it yourself. So, given that installing software is hard, it's okay if you don't all get all of the stuff that we're going to show working right now. Every single thing we're going to show is in a notebook with clear descriptions of what's going on, which you can go through at your leisure now or in the future. So, to see all the materials, you go to juliarobotics.org/tutorials, and you'll get a link to everything you need. Every single thing we do is going to be linked from that site. So that's the only thing you need to remember. So juliarobotics.org/tutorials. Good? All right, cool. So were you to go to that site and get everything set up, the first thing you would see in the set of tutorial notebooks is our introduction to Julia itself. So the way the talk is going to work is I'm going to talk about some of the features of Julia and some of its advantages, and then I'm going to hand it over to Tuan, who's going to show off rigid body dynamics, which is a library that Tuan wrote for efficient dynamics and kinematics algorithms. So sort of the core of robots that move. Okay, but first let's talk about Julia. So Julia is a programming language in the same way that Python is a programming language. Its primary advantage is that it's fast and still relatively expressive. So you can actually write Julia code that runs as fast as C, and we frequently do. On the other hand, the syntax is relatively clean. It kind of looks like Python or MATLAB, so it's possible to sort of write nice high-level code. The whole point of Julia is that we want to solve the two-language problem. So you have to write your code in Python, and then you write it again in C, or you just write it in Julia, and you're done. To be clear, we did not create Julia. We were just very enthusiastic users who have contributed a lot of packages to it, but we know some of the people who did. Okay, so Julia is free. It's open source. It's on GitHub. You can do absolutely anything you want to Julia or with Julia. You can sell it. You can do anything. That's a big advantage over MATLAB. Julia is not anything like ROS. It's just a language, We have some tools that I think will be useful, but we don't have anything near the complexity and feature completeness of ROS or MATLAB. I think that's okay. I think Julia is best if you like breaking things and building new things. Just in case you're wondering, it's not object-oriented, so it's okay. We'll show you how to do stuff. And it's not quite done. So Julia 1.0 is coming out this summer. Things are going to change a little bit. Like every once in a while, I have to update my code. With the release of 1.0, it's going to be a lot more stable. We promise. Okay, so there are instructions for installing Julia. Hopefully you've done that. If you haven't, it's okay. You can just take care of it later. We have everything you need to know. Julia itself, it looks just like the Python command line. You can enter commands. But what we're showing here is actually Jupyter. So if you're familiar with Jupyter notebooks for Python, they're a great way to do interactive computing. They also work great with Julia. In fact, the reason it's called Jupyter, the JU part, is from Julia. So that's what we're going to show because it's a nice way to sort of interleave code and text. And this is actually how I do most of my research as well. Okay, so let's do some basic things in Julia. Basic operations probably look pretty familiar. So addition works, printing works. Julia has built-in support for arrays.
What are you doing to make that happen?
I'm pressing Shift and then Enter. So basically each of these blocks is just a set of code, and Shift Enter is telling Julia run this cell and print the output. So this is a feature of the Jupyter environment, and you do the same thing in Python, for example. Likewise, we can use matrices. Unlike MATLAB, we have really nice support for n-dimensional arrays. They're really just an extension of 1 or 2-dimensional arrays. Indexing into things, pretty similar for MATLAB. It's one indexed, guys. It's okay. Took me a while. Yeah, it's all right. If it's any consolation, it's because Fortran was. Also math, also people, but I won't get into that right now. We can slice things. It has a nice end, just like in MATLAB, to get the last element along a dimension. Okay, so that's all good. But we can do a little more things. So people who use MATLAB might recognize the dot plus, which says plus, but do it element-wise. So we have that in Julia too. But Julia actually extends that. So any function can be dot applied to anything. So we can apply any function element-wise over an array of any number of dimensions or any combination of arrays, and it will sort of broadcast that operation across all of the arguments. So here I'm going to take the sign of every element. So that's nice. Basic linear algebra is similar to MATLAB. We have inverse. So inverse of x times x, well, math tells us that should be the identity. But floating point numbers are a little weird. And if you were to try this in MATLAB or Python, you'd see a similar result where it's very close. It's ones with a lot of really tiny things. That's just something essential to the way floating point math works on computers. Fortunately, Julia, if you really care, has really good support for things like rational numbers. So if I make a rational number using big integers, I can get an exact version of x, of that random matrix. And I can use the inv to take its exact rational inverse, and I get an exact rational result, which is exactly the identity. So Julia has really good support for arbitrary data types, and this is a feature that we're going to use a lot. So passing different data types through the same functions to get new behaviors. Okay, Julia has functions. You can write them. You can call them, kind of like Python. You can pass anything you want into a function. You don't have to specify the types, but you can. And if you want, you can be specific. So you can create a new method for numbers, or an even more specific method for a particular kind of number, like floats. And Julia always picks the most specific method of a particular function. So 5 is just a number, so it says hello 5, number 5. But 5.0, that's a float, so it actually can do something different. And this is actually sort of the core of making things like inverse of rationals actually do something meaningful and cool. We also have a nice short form for functions, which I like a lot for really short things. So that works. Functions return whatever they had last, so it's easy to write a function that just does a single computation. Okay, Julia actually has types. You don't have to deal with them much if you don't want to, but they really can make your life better, and they're ultimately important for performance. So 1.0 is not a 1-by-1 matrix of doubles. It really is a float. 2 is an integer. They're different. It's okay. It's okay. You can convert them. It's real easy. Yeah?
You put 2 into something that would expect a float. Does it do implicit conversion?
No, there's never implicit conversion. If you have a collection of floats, then yes, it will try to convert to the container type. A function that expects a float, and you'd better provide it one. In general, we try not to write functions that are that specific because it reduces sort of the power of the language. We have arrays. Arrays know what kind of elements they contain. You can change those as much as you see fit. So for example, if you expected an array of floats, you got an array of ints, it's easy to convert. You can make your own types. So this is a struct called person, which has a name field and an age field. That's all you need to declare a type. I find this a lot more convenient than creating a new class in Python. A nice thing is that Julia types are extremely lightweight, much, much more so than in Python or MATLAB. So for example, the size of this struct is exactly just a string and an int. There's nothing else there. That's really nice for high performance code. But Julia doesn't, I mean, it's not MATLAB. It doesn't come with 10,000 packages for useful things. But it does have about 10,000 packages available. And the way that you install them is through PKG, the package managing package built into Julia. So for example, if I want to play around with colors, which is one of my favorite little utility packages, I could do package.add colors. If you install the tutorial, you already have this. To activate a package, I just do using. And for example, I can get 10 different distinguishable colors. But maybe I only wanted 5. That's nice. This is a nice feature of Jupyter that it knows how to render colors directly as graphics in the notebook. I can even make a random matrix of RGBs. So a random matrix of colors, well, that should be a matrix of colors. So there we have it. We're rendering random matrices. This is just a regular Julia array, but every element happens to be a color. You can do that. Any kind of package that isn't registered, you can install with clone. So this is how you would have installed our tutorial. Another one of my favorite things about sort of the early parts of converting to Julia is that it's really easy to talk to C, Fortran, and Python code. So in particular, we can call directly into C functions. So libc is the C standard library. If you had your own C library, this is literally all you have to do. Tell it what function, what library, what does it return, what arguments does it need. And there's almost no overhead to do that. So I can use C to compare 2 strings. I don't know why you would, because C is the hardest language to compare strings in, but you could. It's also relatively easy to call Python code. So there's a package called pycall, which provides basic conversions for things like importing Python packages, converting types back and forth. I found this really useful because when I was first developing in Julia, there was nothing. But I had a lot of tools available in Python, and so I could sort of wrap those from Julia and then more and more replace them with Julia. Yeah, Jesper. Yep. There actually are, it's not too bad. Yeah, so there's a package called cxx.jl, which actually provides a CXX C++ REPL, so a C++ terminal where you can interactively enter C++ code that uses Julia's own compilation backend to power it. And you can call into C++ shared libraries, but yeah, the fact that I mean, you have to deal with name mangling at some point. So like, there has to be some involvement of a header file somewhere, or you have to be very, very clear about what you're doing. So it's about as easy as calling into C++ can be, let's say. But Python's real easy, so I'm gonna use pycall, so activate that package. PyImport means import this Python package, and now I can use it just like it's Python. So this is datetime.today, but it's powered by Python. Okay, so that's all pretty cool. Julia works, it's basically functional. But it's really not worth switching to something unless it has some advantage. I think one of the biggest advantages of Julia is that it's fast. So let's check, shall we? Here's an easy function. Let's just try to sum some elements. So yeah. Oh, I'm sorry. You guys. These are just open in different tabs. Yeah. We opened all of these ahead of time. So let's make 10 to the 7th random numbers between 0 and 1. Okay, and let's sum them. So sum is a function that Julia provides, just like Python, and we get a number that's about 0.5 times the number of numbers. Okay, so that's a good sanity check. So let's see how fast it is. There's a Julia package called benchmark tools, which does a little bit better than tick-tock in MATLAB. It actually runs your function a statistically significant number of times and tries to get a real estimate of how long it takes. So I said we could call C code. Let's just write some C code. So I've actually put some C code in a string. Why not? This is just a regular C function. I can tell Julia to run a command line program, like a compiler, and compile some C code. So I'm just going to do that. I'm going to compile that code into a library and make a Julia function that calls my C function. It's kind of magical. And so there it is. So I can run this Julia function, and it's actually calling my C code. It's kind of cool. And we can make sure it gets the right answer. So let's benchmark it. So this is benchmarking calling that C function from Julia. And it's going to run it like 10,000 times, so it might take a second. but it's going to be pretty fast. Yeah, okay, so this took about 8.2 milliseconds. So that's pretty good. That's summing 10 million elements in 8 milliseconds. C is pretty fast. Python, well, let's try it. I don't know. Python has a built-in sum. We can get that, so ask for the Python built-in function called sum. Does it work? Yeah, it works. It returns the right answer. Check it. Yeah, all right, we're good. We can benchmark that too and see how fast that is. Can you turn this back on? Okay, 68 milliseconds. That's a lot slower than C, even though Python's sum itself is written in C. So NumPy's fast, right? So NumPy actually takes advantage of some special instructions in newer processors that can do multiple operations simultaneously. So we can ask for NumPy, check it, benchmark it. All right, I'm going to make sure that everything else is run. I don't want to make you guys wait for me to run benchmarks for every time. Yeah?
Was the C, the raw C version,
Yep.
also optimized for SIMD?
Nope.
Okay,
And that's the difference.
it's an unfair comparison then.
Well, I'm comparing, I have a bunch more comparisons, but yes, that's certainly true. So like if you wanted to write a C version, you would write a different function and you could get it probably down to as fast as NumPy. So NumPy is using SIMD and it's about twice as fast, so that makes sense. Okay, but we could also write it in Python, right? Let's actually see how fast Python is. So this is a Python function. I'm gonna make that available in Julia. It's really slow. Wow, that's really slow. So this was 4 milliseconds in C, in NumPy, and it's 1.5 seconds in Python. Okay, so Python is not good for inner loops, but we knew that. So let's try Julia. So how fast is Julia's sum? 4 milliseconds, so that's just as fast as NumPy. But the difference is it's not written in C. So Julia has a special macro called which lets you see where things are defined. So if you want to find out what sum is, there it is. It's just a Julia function. It reduces plus and combines it with the identity over the array. And these are all, this map reduce, that's just another Julia function. It's Julia all the way down, but it's just as fast as NumPy's heavily optimized C version. And in fact, we can write Julia code that's just as fast as C. So here's a naive version. It's exactly the same thing we wrote in C, but we're in Julia. Benchmark that, 8 milliseconds, which is just as fast as the unfair C version was. Okay, but what if we want it to be really, really good? Like how much work does it take to turn this into the best SIMD optimized version we can? It's that much work. We tell it, please use SIMD. That's the difference. That's it. And it's 4.0 milliseconds, a little bit faster than NumPy, which, to be fair, we had to spend a little time getting in and out of NumPy. So we can get performance that's as good as the best C implementation with syntax that's still relatively readable. So I think that's pretty cool. And the last thing that I want to cover before I hand it over to Tuan is the sort of fundamental power of the way Julia organizes functions and types. So I mentioned at the beginning that Julia is not object-oriented, and that was like very concerning for me because I mostly spent my life programming in Python, which definitely is, or at least is often written that way. So Julia uses something different. Specifically, it uses this thing called multiple dispatch. And this seems like a very technical point, but I think that the more I use Julia, the more I realize that it's actually really important in making things like fast numeric libraries, easy access to derivatives, easy passing of symbolic types, sort of writing a function once and using it to do a lot of different useful things. Okay, so what do I mean? In a lot of languages, you'll do something like call a function f with arguments a, b, and c. So for example, in Python, you could write this. And what this does is, no matter what a, b, or c is, it's always the same function f. So it's always sort of going to do roughly the same thing. Or in Python, maybe it's a method. So a could be a class, and you do a.f. And so now which f you get depends on what a was. But it doesn't care about b or c. Okay, so in Julia, the difference is f of a, b, and c picks the right implementation of f, the one that you specified, based on all of the arguments. So the first one isn't special. None of them are special. What it does is it picks the most specific version of f that applies to whatever you happen to pass in, and then it compiles a specialized version of that function as soon as you need it. So the result is that no matter what a, b, and c are, you get the right implementation and you get fast native code. Okay, but this is all just words. So let's try to solve a real problem. So this is a brief aside into a little bit of math. I want to talk about derivatives, not in the money sense, but in the gradient sense. So fundamental to what a lot of us do is optimization. So I have a function, I want to find a way to make that function better. An important part of that is knowing how that function changes as I change the inputs. So for that we need basic calculus. We need to be able to take the derivative of the function. Most of the time in code, when we take derivatives, we do it in kind of a silly way. So if we want to find the derivative of f, we often do it by writing out the derivative by hand, which means doing calculus in your head or on paper, and then writing down the result of that calculus in code, and hoping you got it right, writing tests to make sure you got it right, and never changing anything ever. And I've spent a lot of my life getting derivatives wrong, or subtly changing the original algorithm and not updating the derivative, and having them not match and give bad answers. And this just isn't great. So people who don't like writing down calculus by hand might try numerically differentiating. So I mean, we know the definition of a derivative is just perturb the input a little bit, subtract off the original, and divide by the amount that you perturbed. Right? This is like very basic calculus. You can do this in code, but the problem is that this is only true in the limit as this perturbation goes to 0. And there's an awkward feature that computer math, especially floating point math on computers, becomes progressively less accurate as your numbers differ in scale. So in particular, as your perturbation goes to 0, the accuracy of the fundamental math you're doing on a computer decreases. So not only is this somewhat slow, you have to call the function at least twice, it actually tends to give the wrong answer. So there's a better way, which is automatic differentiation. So automatic differentiation relies on generally passing some kind of special data type through your function that knows how to track its own derivatives. And you implement a few basic operations to do basic calculus and the chain, and then you get derivatives of anything you want relatively efficiently and without writing any more code. So let's do it. So I'm going to make a structure. It's called a dual number. So it's dual because it knows its value and its derivative. So I've declared a new type, and I made one. This parameter means it can take any kind of internal scalar type. So I can make one that has a float inside or an int inside, and I'll get efficient code for both kinds. Okay, so if we want to implement math on these, we simply import the function we want to describe. So I want to make plus work. I want to implement addition and track derivatives. So plus is just a regular Julia function. It knows how to do a lot of things already. It knows how to add bools to bools. It knows how to add big floats to other big floats. It knows how to do all sorts of interesting things. But it doesn't know how to do what I want. So I'm going to teach it. I'm going to tell Julia that you can add numbers to duals by adding their values. You can add duals to numbers in the same way. And if you have two dual numbers, we do a little bit of basic calculus, and we remember that you just add their derivatives. So that's it. And now I have addition working for anything which is any kind of number. So all of the built-in Julia number types. So now we can add a number to a dual, and it propagates the derivative correctly. I can add duals to each other, and their derivatives combine. Okay, but addition's not very interesting, so let's do multiplication. So this is literally just the product rule. So to multiply two duals, you multiply their values, and their derivatives obey exactly the product rule. Okay, so now that we've done this, that's it. We now know how to add and multiply and track derivatives. Okay, but you can overload operators in C++, so what's the difference? The difference is that there's nothing special about operators. Every function in Julia works this way. They're all the same. So I can implement sines and cosines just as easily. So to take the sine of something and track its derivative, you just remember that the derivative of sine is cosine. And likewise, the derivative of cosine is negative sine. Okay, so now we have addition, multiplication, and trigonometry. So now, yeah, Mike.
How do you extend this to vectors?
So you could, for example, write another version of sine that takes a vector of duals. But you typically wouldn't. Typically what you would do is, for example, make a vector and then apply sine element-wise. And that works. So because I know how to do the scalar type, I get vectorization for free.
But now you do something special to, like, say, collection gradient.
Sure. Yeah. I mean, I'll go into. I'm not going to go into like the full multidimensional version of this, but yeah. I mean, I can sort of show you offline. But like, yes, at some point you do have to decide: are you taking vectors, or what are you doing, and like, how do you handle them?
Is a vector rule?
Yeah. Yeah.
It feels like forward mode of automatic differentiation.
Yeah.
Would that be specification?
Yeah, so this is, you're exactly right. This is forward mode automatic differentiation, which is very efficient when you have more outputs than inputs. That's often the case in robotics. There's another entire version called reverse mode, and Julia actually has very good packages for both. So you can choose forward or reverse, and actually you can mix and match. So you can use a reverse mode algorithm with some forward mode kernels inside. I'm not going to get into that right now, though, but it's pretty cool. Okay, but let's define a function that sort of combines all the pieces. So to evaluate the derivative, we can construct a new dual number, and its derivative with respect to itself is 1, because dx is 1. And so if we pass that through our function, and then ask for the derivative of the result, we get the derivative of the function itself. So that's it. We've done calculus. By just implementing enough of the chain rule, and the product rule, and the addition rule, we get calculus of anything that involves those components. And the nice thing is that this answer is exact up to whatever your computer can do in terms of floating point precision. We can try numerical differentiation, so estimate by perturbing a little bit, like 10 to the minus 8, and we get a very similar answer, but it's not quite right. Okay, so that's pretty cool. But
So how much is to make a whole auto differentiation track?
yeah.
It's like you say 50 lines of code.
No, honestly, I mean, implementing all of the primitives is one part. Making it efficient is another part. Fortunately, I didn't have to, because someone who sits upstairs from me in MIT has already done it, and it's available, and you can package.add it right now. But a big difference is that doing something like this in Python would be really hard, and also tremendously slow. And I'm going to show right now that it's actually pretty efficient to do this in Julia. So my original function took 16 nanoseconds. My dual version that's tracking derivatives took 33 nanoseconds. And it's basically because to compute the value and the derivative, I did a sine and a cosine. So it took twice as long. But like, that's 16 nanoseconds. That's really not a lot. And that included constructing that type, unpacking it, sending it through the right functions, looking up all those definitions, and running everything. So there's basically no overhead introduced by this type. Okay, so remember we defined multiplication. Well, that means we get power for free. And we defined addition. So, well, sum just calls addition a bunch of times, so we get sum for free. So anything that is built out of the primitives we've already defined, it just works. So now I'm going to write a function called derivative that's going to take a function as its argument and a value, make a dual, call the function, grab the derivative, and now I've finished calculus. So the derivative of f at pi over 4 is this value. Make another function. What's the derivative of x squared at 2? I hope it's 4. It's 4. What's the, we can check that against the right answer. What's the derivative of 3x plus sine of x squared times 10 plus cosine of x? Quick, 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 it's that. Okay, and we can check that against the one I wrote out by hand. I hope I got it right. I did. Julia functions can be arguments to functions, and they can also be returned. So anonymous functions in Julia are fast. So I can even make a derivative that takes a function and returns a new function. So now I have df. That's the derivative of my function f. And I can ask for its value. So that's the derivative of f at pi over 4. And if you've used MATLAB, you'll be scared because anonymous functions in MATLAB are tremendously slow. So let's check. 33 nanoseconds. So there's no overhead to any of this implementation. So now we have a nice generic derivative function that doesn't cost us anything to use. So we didn't have to do much to get this. Now, if you tried to ask for the log of something, I haven't implemented that yet. You'd need to add another definition that says the derivative of log is 1 over x. Likewise, the derivative of e to the x is e to the x. But in general, we can sort of build a few basic building blocks and put them together to create a whole lot of useful behaviors, and it's not tremendously slow. Yeah?
If you try to get the derivative of something you haven't defined, it tells you.
Yeah, let me show you.